Next, we are going to discuss two important topics in thermochemistry called internal energy and enthalpy. In order to understand internal energy and enthalpy, we need to first review a little bit about the first law of thermodynamics, some concepts about heat and work, and then pressure changes in our system, which could either be contraction or expansion. This will give us the background to discuss internal energy and enthalpy. To begin our discussion of internal energy, recall that the bonds within chemical substances are storing potential energy between them. When a chemical reaction occurs and reactants are converted into products, the bonds of the reactants must be broken, and that requires energy. Therefore, it's an endothermic process. When new bonds are formed when we make our products, that's an exothermic process, as making new bonds releases energy. The molecules within a system can undergo different types of movements that also creates different types of kinetic energies as well, such as vibrational movements, where the molecules can undergo different types of stretching, twisting, or rocking motions. They can undergo rotational movements, where they're moving, and translational movements as well. There are more different types of kinetic energies that the molecules can have, but these are just a few of them. The internal energy of the system is the sum of all of the total potential and kinetic energies of the particles that form the system. Therefore, it's the total of all of the possible kinds of energy present in a substance. We use the symbol capital U to describe internal energy. Usually the internal energy cannot be measured directly, but the internal energy of a system is directly proportional to the temperature of that system. Therefore, if the temperature of a system increases, the internal energy also increases. If the temperature of a system decreases, the internal energy of a system decreases as well. Energy can be stored in the form of work or heat, and we can exchange heat and work between a system and its surroundings. Both of those will be related to the internal energy change of a system. Therefore, delta U, or internal energy change, is equal to the sum of the heat changes plus the work changes of our system. There are a few different signs we'll see, and they're just telling us the direction of flow for heat and work. If heat is transferred into the system from the surroundings, so Q going in, that would mean we would have a positive value for our heat. If heat is leaving the system and going out to the surroundings, the Q value would be negative. The same concept applies to work. If work is being done on the system by the surroundings, we would have a positive value for our work. And if work is leaving the system, because the system is doing work on the surroundings, we would have a negative value for our work. So all the signs on our heat and work tell us is the direction of flow for that energy change. Now we have already briefly discussed the first law of thermodynamics, but we're going to revisit it in terms of internal energy. The law of conservation of energy stated that energy could not be created or destroyed, but it could be transferred from the system to the surroundings, or it could change forms. Therefore, the internal energy of the system plus the internal energy of the surroundings must equal zero if the energy of the universe is always constant. We could rewrite this and say that the internal energy of the system will be equal and opposite in sign to the internal energy of the surroundings, because energy can be transferred from system to surroundings or from surroundings to system. This is the law of conservation of energy. The first law of thermodynamics essentially tells us the same thing, but it's rewritten in order to discuss the heat and work changes. The first law of thermodynamics states that the change in internal energy of an isolated system is equal to the sum of the heat gained or lost by the system and the work done on or by the system. Therefore, the internal energy of the system, or delta U subsystem, is equal to Q plus W. Both of these things, the law of conservation of energy and the first law of thermodynamics, are essentially saying the same thing, but in two different ways. The energy of the universe is constant. Up until now, we've only been considering the heat changes associated with chemical reactions. When energy is produced in a chemical reaction, some of it could be dissipated as heat and some of it could be used to do work. This is usually only relevant in reactions where there is a large number of change in the moles of gaseous reactants to gaseous products. Work is equal to a force times the distance. We could calculate the work by taking the negative of the external atmospheric pressure, or P, times delta V, the change in the volume of gases, where delta V is equal to V final minus V initial, or some final volume minus some initial volume. Pressure volume work occurs when a system pushes back against the surroundings, or when the surroundings compress the system. This is referred to as expansion work or contraction work. If we imagine we have a reaction that has gases in it, and we have an imaginary piston pushing down on those gases. When we're going from reactants to products, notice that the piston is compressing the gases. That would be an example of forming less gases as a product than we had as a reactant. In this example, since the surroundings are pushing down on the system, the work would be a positive value because the surroundings are doing work on the system. This would be an example of contraction work. In expansion work, the piston would be moving up away from the system and doing work on the surroundings. In that case, work would be negative. Internal energy is an example of something called a state function. A state function is a property that only depends on the state of the system at any moment in time, and not the path used to get that system to the state. That means we only are interested in the initial and the final state. It's path independent, we would say. Imagine that you have two different paths you could take to get from the bottom to the top of a mountain. If you take X and walk straight up the mountain, you'll have started at the base and made it to the summit. Or you could take path Y. You still have started and ended at the same location. That would be an example of a state function. State functions are usually represented by capital letters. Temperature and internal energy are two examples of state functions. Since temperature and internal energy are directly proportional to one another, it makes sense that both of them are path independent. That means in order to calculate internal energy, if we knew the final internal energy, or the internal energy of our products, and we subtracted off our initial internal energy, or the internal energy of our reactants, we could calculate delta U, or the difference in internal energy. If a reaction is done at a set of conditions where no work is done by the system or the surroundings, then the heat evolved or absorbed would be equal to the change in the internal energy of the system. Recall that delta U is equal to the heat plus the work changes. If we're saying that no work is done, then the internal energy would just be equal to the heat either absorbed or evolved by a reaction. So if we set work to 0, we can say that delta U would equal Q plus 0, and therefore delta U would be equal to Q, or the heat. In order to achieve no work being done, a reaction could be run at constant volume. Therefore, we can rewrite this equation to say delta U will equal Q sub V, meaning heat at constant volume. The easiest way to run a reaction at constant volume is to complete it inside of a bomb calorimeter. A bomb calorimeter allows for constant volume because the reaction container is sealed. Therefore, even if gases are generated, the reaction container cannot expand or contract because it's made out of steel. Therefore, internal energy can be redefined as the heat of reaction that's calculated at constant volume conditions. Many of our experiments are not carried out at constant volume. We usually don't work inside of a bomb calorimeter daily in the lab. Most of our reactions are carried out on the open benchtop where we're working at constant pressure instead of constant volume. Therefore, if we generate a lot of gases in a reaction, some of our heat energy could be converted to work. This brings us to a concept called enthalpy. Enthalpy is defined as the sum of a system's internal energy and the mathematical product of its pressure times its volume. Enthalpy is also a state function. That means that we don't measure enthalpy directly. Instead, we only measure enthalpy changes. So from here on forward, we'll talk about delta H to refer to the change in enthalpy. Since enthalpy is a state function, we can rewrite our equation as the change in enthalpy is equal to the change in internal energy plus the pressure times the change in volume of the system. We talked about how our change in internal energy is equal to the heat plus the work changes. We will write Q sub P instead of just Q to represent that we're talking about a system at constant pressure. Our external constant pressure would be the same when we're working in an open benchtop situation. Work is equal to negative P times delta V. Therefore, if we multiply the equation through by -1, we could say that negative work is equal to pressure times the change in volume. If we make these substitutions into our enthalpy equation, we can say that our delta U is equal to Q sub P plus W, and our pressure times change in volume is equal to negative W. This allows us to cancel out our work terms, and we're left with delta H is equal to Q sub P. What that means is that the enthalpy change, delta H, is the heat of a reaction at constant pressure. Since enthalpy is also a state function and we don't measure it directly, we only measure changes, we can say that the delta H is equal to H final minus H initial, or in terms of a chemical reaction, the heat of the products minus the heat of the reactants. For an endothermic reaction, the enthalpy will be equal to a positive value. For an exothermic reaction, the enthalpy will be equal to a negative value. Let's summarize the concepts we discussed. The heat given off or absorbed when a reaction is run at constant volume is equal to the change in the internal energy of the system. Delta U system is equal to Q sub V, where delta U is equal to internal energy and Q sub V means heat at constant volume. 2. The heat given off or absorbed when a reaction is run at constant pressure is equal to the change in the enthalpy of the system, where delta H system is equal to Q sub P. Delta H represents the enthalpy, and Q sub P means heat at constant pressure. 3. The change in the enthalpy of the system during a chemical reaction is equal to the change in the internal energy plus the change in the product of the pressure of the gas of the system and its volume. Delta H system is equal to delta U system plus P times delta V. This is our link between enthalpy and internal energy if we needed to convert between either form. 4. The difference between delta U and delta H for the system is small for reactions that involve only liquids and solids, because there is very little change in the volume of the system during the reaction. The difference between enthalpy and internal energy can be very large for reactions that involve gases if there is a change in the number of moles of gas during the course of the reaction when we go from reactants to products. So that means that sometimes delta H and delta U could be just about the same, and sometimes they'll be entirely different depending upon how the reaction was carried out, whether it was at constant pressure or at constant volume. Next, we're going to learn about reading thermochemical equations. Imagine we have the combustion of octane, which is the primary component of gasoline, and we are given this balanced equation. Originally, we said that this combustion is exothermic, therefore it releases energy. Some of the energy could be in the form of work, some of the energy could be in the form of heat. We're going to go back to focusing on the heat of the reaction, or in other words, the enthalpy of it. Writing heat at the end of a thermochemical equation is not the proper way to represent the energy change. What we want to do is list the balanced chemical equation followed by the delta H on the right-hand side. The delta H represents the enthalpy of this reaction. So therefore, when 2 moles of octane are combusted, 5,000 kilojoules of heat are released. Recall that the negative sign out front means that heat is given off as a product. Therefore, the temperature would go up. Energy was released as a result of this process. Enthalpy change is represented by delta H, and the superscript naught symbol that you see means that this reaction was ran at standard state conditions when that enthalpy value was measured. We'll talk about what those standard state conditions are in a few minutes. We can use our balanced chemical equation along with the enthalpy change listed in order to write some conversion factors. The reaction listed involves the number of moles specified by the balanced chemical equation. Therefore, what that means is only when 2 moles of octane, C8H18, are combusted is 5,220 kilojoules of heat released. Or when 25 moles of oxygen are used in this reaction, then and only then is 5,220 kilojoules of heat released. We could say the same for our products as well. When 8 moles of carbon dioxide are formed, the amount of energy specified by the balanced chemical equation is released. That amount of energy does not hold true unless we have the exact molar coefficients listed in the balanced chemical equation reacting or being formed. When reading a thermochemical equation, the amount of energy that's listed only corresponds to the balanced chemical equation. This means that when 1 nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia, 92.4 kilojoules of heat is generated, and it's released because the reaction is exothermic. If we were to change the amount of nitrogen or hydrogen that reacts, we would change the amount of energy that's released. Whenever we list a thermochemical equation, we must also include the physical states. If we were to form something in a liquid form instead of a gaseous form, the amount of energy of that reaction would change as well. Imagine if we took our ammonia synthesis and we multiplied everything through by 2, and we had 2 moles of nitrogen reacting with 6 moles of hydrogen to produce 4 moles of ammonia. Then the amount of energy that's produced would double as well. We would produce 185 kilojoules of heat because we would also have to multiply our enthalpy through by 2 as well. If we were to take our reaction and cut it in half, where we only had 1/2 of a mole of nitrogen reacting with 3/2 of a mole of hydrogen to form 1 mole of NH3, the amount of energy produced would be 46 kilojoules, or half of our initial amount. Therefore, the delta H that you see listed after a thermochemical equation only corresponds to the mole ratios out in front for that balanced equation that it's written for. You often will see fractions because the fractions are representing moles only and not molecules. Therefore, we don't have a half a molecule of nitrogen, but we could have a half a mole because a mole is just a counting term. They're only representing the molar ratios for that balanced chemical equation. Often the enthalpy that's calculated is referred to as the standard enthalpy of reaction or standard heat of reaction, written as delta H with a superscript naught symbol at the top. This superscript 0 that you see indicates something called standard state conditions, meaning that a reaction was carried out with a certain temperature, pressure, and concentration of solution in order to be able to reproduce it at any time. The standard state conditions that are used are 1 atmosphere of pressure for gases. If we have an aqueous solution, the concentration is 1 molar, and the temperature is usually specified, but it's often at 25 degrees Celsius, which would be 298 Kelvin. These are the conditions implied when you see that superscript 0 after the enthalpy. How much heat in kilojoules is liberated by the combustion of 6.54 grams of magnesium? We have our balanced thermochemical equation. 2 moles of magnesium react with 1 mole of oxygen to produce 2 moles of magnesium oxide. The enthalpy of reaction is negative 1,203 kilojoules. Now recall that the value that's given for our enthalpy only corresponds when 2 moles of magnesium are combusted and reacted with 1 mole of oxygen. We want to know how much heat is given off specifically when we have the combustion of 6.54 grams of magnesium. So we can use our thermochemical equation in order to write a conversion factor. 6.54 grams of magnesium, but in order to use our balanced equation, we're going to need to convert our grams of magnesium into moles of magnesium. And looking at the periodic table, 1 mole of magnesium has an atomic mass of 24.3 grams. Right now, our grams of magnesium cancel and we're in moles of magnesium. We're interested in calculating the amount of heat in kilojoules. We can write a conversion factor between our moles of magnesium and our delta H that we were given. What that says is when 2 moles of magnesium are combusted, negative 1,203 kilojoules of heat are released. Therefore, from our balanced equation, 2 moles of magnesium is equivalent to negative 1,203 kilojoules of energy. Our moles of magnesium will cancel and will be left in units of kilojoules. And we still expect it to be negative because it's still an exothermic reaction. We're just going to get a smaller amount because we don't have 2 moles of magnesium. Negative 161.9 kilojoules is the amount of energy in the form of heat that will be released when 6.54 grams is combusted. Methane burns with oxygen to produce carbon dioxide and water as a gas. We have our balanced thermochemical equation, and when 1 mole of methane combines with 2 moles of oxygen, the amount of energy that's released is negative 802 kilojoules. How much methane in grams must be burned to release 432 kilojoules of heat? When we see the word release, what that's telling us is that the sign on our heat is going to be negative. So we want to form only 432 kilojoules of heat. We have to start with what we were supplied with in the problem, negative 432 kilojoules. We want to use our balanced thermochemical equation in order to go from our delta H to our amount of methane. So we're going to work back to the CH4. We know that when 1 mole of methane is combusted, we release 802 kilojoules of energy from every 1 mole of CH4. Now we can see that our kilojoules have canceled and we're in moles of methane. Lastly, we want to get grams, so we're going to use the molar mass of methane in order to convert to grams. 1 mole of CH4 is equal to 16 grams. Our moles of CH4 cancel, our units are left in grams, and we should get 8.62 grams of methane in order to release 432 kilojoules of heat. Next, we're going to learn 2 more ways that we could calculate the enthalpy of a reaction. The first is using standard enthalpies of formation. The standard enthalpy of formation is abbreviated as delta H naught sub F. The sub F means formation. This is the enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from elements in their most stable standard states and under those standard state conditions we discussed earlier. The standard state conditions were for gases 1 atmosphere pressure, for aqueous solutions 1 molar concentration, and they had to be in their most stable physical form and state. We can write the enthalpy of formation equation for forming any substance. What is the enthalpy of formation for the formation of water? So we know what our product is going to be. It's going to be liquid water, and we only want to form specifically 1 mole of the substance from elements in their most stable standard states. So standard state means how do they occur naturally? Hydrogen and oxygen are the 2 elements that are composing water. So we know that we're going to have some hydrogen, and hydrogen is a diatomic gas. And we're also going to have some oxygen, which is also naturally occurring as a diatomic gas. Next, we have to balance this, but because we're restricted to forming 1 mole of water, we often are going to have to use fractions in order to balance the items on the left. H2 is balanced with a 1 out in front, but we only want 1 oxygen, and we have O2 on the left. So we're going to have to write 1/2 out in front of our O2. This would represent the enthalpy of formation for water from elements in their most stable standard states. And we're only making 1 mole of the substance. What is the enthalpy of formation equation for the formation of nitric acid? So our product is going to be 1 mole of the nitric acid, 1 mole of HNO3, and we look and see what elements are making up nitric acid. We've got hydrogen, which occurs naturally as H2 gas. We've got nitrogen, which occurs naturally as N2 gas. And we've got some oxygen, which occurs naturally as O2 gas. All 3 of those just happen to be diatomic molecules. And our hydrogen, we only have 1 H on the right and we have 2 on the left. So we're going to need to put a 1/2 out in front of our hydrogen. Same thing with our nitrogen. We have 1 nitrogen on the right and 2 on the left. So if we list 1/2 in front of it, that'll be balanced. And we have 3 oxygens on the right and we only have 2 on the left, and we want them to be the same. So we can list 3/2 out in front of our oxygen. This would be our enthalpy of formation equation for forming 1 mole of our nitric acid from elements in their most stable standard states. Write a thermochemical equation that would represent the standard enthalpy of formation of sodium bicarbonate. Sodium bicarbonate is NaHCO3 solid, and we're going to make 1 mole of the substance from the elements in their standard states. So we're going to have some sodium, and that is a solid. Hydrogen occurs as H2 gas. Carbon would be a solid. And then lastly, we have oxygen, which is O2 gas. We want to balance everything. We would have a 1 in front of our sodium, a 1/2 in front of our hydrogen, a 1 in front of our carbon, and 3/2 in front of our oxygen, because we're restricted to forming 1 mole of our sodium bicarbonate. Anytime 1 mole of a substance is formed from elements in their standard state, the energy either given off or absorbed by that reaction has been tabulated and can be looked up from a reference source. These standard enthalpies of formation for substances can then be used in order to calculate the enthalpy of a reaction that we might be interested in without actually going into the lab and doing an enthalpy experiment. Notice that the enthalpy for just substances in their most stable standard states by themselves are all 0, such as silver or carbon. Also, diatomic molecules, I2 is 0, N2 is 0. These are assigned 0, kind of like a thermochemical sea level. Therefore, when they combine with something else to make a new compound, then we measure the energy change forming that compound, since enthalpies cannot be measured directly, but we can only measure changes. Large negative delta H of formations means that a lot of energy was released when forming that substance, and it's very stable. Some enthalpies are also positive, which means that energy must have been increased and put into the system in order to form that substance. You will be given a table that tells you the heats of formation for typical substances, as long as you know how to use them. There's a lot of reference data in the back of your textbook as well, and there's a large handout on Blackboard that you can print off and use while you're working on your homework. We're going to use these values in order to calculate the standard heat of formation for some reactions next. Hess's law equation says that the standard enthalpies of formation can be used in order to figure out what the heat of a reaction is without manipulating any thermochemical equations or doing an actual experiment. We can figure out the heat of the reaction by taking the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants and multiply by any coefficients from the balanced equation. So our little n symbol represents those coefficients that we would multiply by. Heats of formation are measured in units of kilojoules per mole, and when we multiply by the coefficients, which are mole ratios, the moles will cancel and we'll just end up with units of kilojoules for our heat of our reaction. The heat of our reaction could be positive as in endothermic, or it could be negative as in exothermic. When baking soda is heated, it decomposes. 2 moles of sodium bicarbonate, or baking soda, break down to give us 1 mole of sodium carbonate, 1 mole of liquid water, and 1 mole of carbon dioxide gas. Use the standard enthalpies of formation to calculate the heat of this reaction in units of kilojoules. So in order to do this, we're going to use Hess's law of summation that says that the heat of reaction is equal to the sum of the enthalpies of formation of the products minus the sum of enthalpies of formation of the reactants times any moles from the balanced chemical equation. So our heat of our reaction, often abbreviated delta H sub reaction, will be equal to 1 mole times the heat of formation for our sodium carbonate plus 1 mole times the heat of formation for our water plus 1 mole times the heat of formation for carbon dioxide. That will take care of the sum of our products. Now we're going to subtract the sum of our reactants. For our sodium bicarbonate, there's a 2 out in front, so we're going to have 2 moles times the heat of formation for our NaHCO3. We can look up on our standard enthalpy of formation chart what the actual values are and plug them in to this equation to calculate the overall heat of our reaction. So the heat of our reaction will be equal to, we have 1 mole times the heat of formation for sodium carbonate, which is negative 393.5 kilojoules per mole, plus 1 mole for our liquid water times the heat of formation for water, which is negative 285.9 kilojoules per mole. Notice that there's 2 values listed on your enthalpy of formation chart, one for liquid water and one for gaseous water. That's why you want to be sure to keep track of the states of matter. 1 mole for carbon dioxide times the heat of formation for carbon dioxide, which is negative 1,131 kilojoules per mole. That's going to be the sum of our products. Notice that the moles cancel when we multiply by the coefficient from the balanced equation, and we're just left with kilojoules. We're going to subtract off the sum of the heat of our reactants. We have 2 moles times the heat of formation for our baking soda, which is negative 94.77 kilojoules per mole. So the heat of our reaction should come out to be positive 85 kilojoules. So our positive sign tells us that this must be an endothermic reaction, one where energy is needed to be put into the system in order to drive it from reactants to products in the first place. Let's try another example. Use the enthalpies of formation to calculate the heat of the reaction for calcium chloride combining with sulfuric acid to form calcium sulfate and hydrogen chloride gas. So we are going to take the sum of our products minus the sum of our reactants, and the only substance that has a coefficient out in front of it other than 1 is the hydrogen chloride gas, or we have a 2 out in front of it. So for our heat of our reaction, delta H of reaction at standard state conditions, we can calculate that by taking 1 mole times our heat of formation for our calcium sulfate plus 2 moles times our heat of formation for our hydrogen chloride gas. That'll be the sum of our products. And we're going to subtract off the sum of our reactants. 1 mole times our heat of formation for calcium chloride plus 1 mole times the heat of formation for our sulfuric acid. So now we're going to look at our heat of formation chart and actually look up what those values are. The change in enthalpy for our reaction will be equal to 1 mole times our value for calcium sulfate is negative 1,432.7 kilojoules per mole plus 2 moles times our heat of formation for hydrogen chloride gas, which is negative 92.3 kilojoules per mole, minus the sum of our reactants. We have 1 mole times the heat of formation for our calcium chloride, which is negative 795 kilojoules per mole, plus, last but not least, 1 mole times our heat of formation for sulfuric acid, which is negative 811.3 kilojoules per mole. When we plug that all in to calculate our enthalpy change for our reaction, we should get about negative 11 kilojoules. So this reaction was exothermic because we got a negative delta H. And notice in each case, all of our moles cancel when we multiply by the coefficients from the balanced equation. So our units are just kilojoules that we're left with. The last way that we're going to learn about calculating the enthalpy change of a reaction is by using Hess's law. Enthalpy is a state function we learned, so that means that it's path independent. All that matters is the initial state and the final state. We can determine the enthalpy change of a reaction by measuring it experimentally, or we could use the heat of formation values that we used in our last 2 examples. We could also use other experiments that were ran and we determined the enthalpy changes from them and manipulate them to add up to some overall equation of interest. If we have a reaction that's not easy to carry out in the lab and measure thermochemical data, using Hess's law is probably the best bet. If we can write a process as the sum of several stepwise processes, the enthalpy change for that total process will equal the sum of the enthalpy changes for all of those various steps. Let's compare 2 separate processes and see how Hess's law would work. We could have a direct process, which would mean going directly from reactants to products. Imagine we have carbon combining with oxygen to form carbon dioxide. If we did that reaction, we could measure the enthalpy change directly as negative 394 kilojoules. Or we could do a stepwise process. We could first combine 1 mole of carbon with a half mole of oxygen to form carbon monoxide gas and measure the enthalpy change associated with that step. Then we could react carbon monoxide gas with a half mole of oxygen to form carbon dioxide, which was our initial product in the first direct process. If we know the enthalpy change for these steps that we did in the stepwise process, we could add them together to determine the overall enthalpy change. Notice that our carbon monoxide is present on the right-hand side and the left-hand side of both of our steps. Therefore, we can think about it like it cancels. The 1/2 O2 plus the other 1/2 O2 would add up to 1 O2. And what we were left with is our reaction that was the same as our direct process. Therefore, the sum of the enthalpy changes for both steps will add up to being the exact same enthalpy, whether we did it directly or we did it stepwise. Since both of those canceled, they're no longer in the overall equation. And our enthalpies was the sum of those individual steps. If we were to look at this in terms of an energy diagram, we could think about it if we started with carbon and oxygen and we combined them together directly to form our CO2, almost 400 kilojoules of heat would be released. But if we only combined 1/2 a mole of oxygen instead, we would form the carbon monoxide and 111 kilojoules of energy were released. Then when our carbon monoxide combined with another 1/2 mole of oxygen, 283 kilojoules of energy were released, and we finally got to that same product of carbon dioxide. So this is what Hess's law says. It doesn't matter if the reaction occurs in one step or a series of steps. If we can get the series of steps to add up to the overall equation that we're interested in studying, we can manipulate the individual enthalpies and the individual equations to get them to add up to what we want them to. There are a few things that we can do in order to manipulate thermochemical equations. We could flip a reaction around and write the reactants as products and the products as reactants. If we do that, we have to flip the sign on the enthalpy change. Positive would become negative and negative would become positive. We could multiply or divide through by a coefficient, and we would also have to multiply and divide through by the enthalpy change. And we can add up all the reactions, and then we add up the values of delta H. Use the following information to calculate the change in enthalpy for the combustion of methane. We have 1 mole of methane reacting with 2 moles of oxygen to form 1 mole of carbon dioxide and 1 mole of liquid, 2 moles of liquid water. We're given 3 thermochemical equations that we can use in order to add up to our overall equation of interest. And so a few things that I look for is I try to place the reactants on the correct side and the products on the correct side, and I like to try to cancel anything that is not. Also check the coefficients. You want your coefficients to match as well. So in equation number 1, for example, notice that methane, CH4, is on the left. And it's on the left right here as well, so that tells me I probably don't want to flip this equation. Also, they both have a coefficient of 1 out front, which is what we want. So we're probably not going to want to multiply or divide through by anything either. Let's leave this first equation the same. In the second equation, we can see that we have this CH2O intermediate that's not present in our overall equation that we're trying to target. Therefore, this is going to be something we want to end up canceling. It's on the left in the second equation, and it's on the right in the first equation. As it is right now, they both have a coefficient of 1, so they would end up canceling each other out. Also, our CO2 is a product, and it's a product in our overall equation, and it has a coefficient of 1. So we're probably not going to want to do anything to the second equation either. We can leave that the same. For our third equation, we can see that we have liquid water, and it's on the reactant side. But in our overall equation, we want our water to be on the right-hand side or the product side. We also want a coefficient of 2 out in front of it. So we're going to want to flip this equation around, and we're going to want to multiply it through by 2. So if we rewrite this, that means we're going to have 2 H2O gas going to 2 H2O liquid. And what we do to the equation, we also have to do to the enthalpy change. So it was positive 44. When we flipped it, it would become negative 44. And then when we multiply it through by 2, we're going to end up having negative 2 times 44 kilojoules, which will be equal to negative 88 kilojoules for our manipulated equation. So now we can think about ignoring number 3 because we rewrote it down here. Looking at equations 1, 2, and 3, now if we check, our water will also cancel as well, our gaseous water, because we have 2 moles of gaseous water on the reactant side, and we have 2 moles of gaseous water on the product side. So both of those are going to cancel. We didn't want those in our overall equation anyways. And what we're left with should be our equation at the top. We have 1 mole of CH4, and that's a gas. We have 2 moles of O2 gas, one in equation 1 and one in equation 2. Our products, we have 1 mole of CO2 gas, and we have 2 moles of liquid H2O. So everything cancels that we wanted it to. Now to calculate the enthalpy change for this reaction, we're going to add up our enthalpy change from number 1, number 2, and then our manipulated number 3. And the sum of those will give us negative 890 kilojoules, which is what we were trying to calculate for our overall equation of interest. Let's try another example. Determine the enthalpy change for the reaction solid carbon plus gaseous water forming carbon monoxide gas and hydrogen gas. We have our 3 thermochemical equations, and we want to get them to add up to our overall equation at the very top. So we're going to have to think about what we're going to do to each of them. Starting with the first one, I first noticed that I have carbon with a coefficient of 1 on the left, and I want carbon with a coefficient of 1 on the left. So I'm probably going to end up leaving this one the same. For my second equation, right away I'm noticing that I have carbon monoxide on the reactant side, but I want carbon monoxide on the product side. I also don't want it to have a coefficient of 2. I want it to have a coefficient of 1. So I'm probably going to have to flip this equation to get my carbon monoxide over to the product side, and it looks like I'm going to have to divide everything through by 2. So let's rewrite our first equation down here. We have carbon plus oxygen going to carbon dioxide. Our delta H is going to be the same. We didn't change that one. Negative 393.5 kilojoules. Our second equation, we want to flip that one around and divide everything by 2. So our products will become our reactants. We're going to have 1 mole of CO2 going to 1 mole of CO plus 1/2 mole of O2. Our delta H is going to be, it was negative 566 kilojoules, and we're going to want to make our negative positive and divide that by 2, and so that will end up being positive 283 kilojoules when we make the changes. And for our third equation, we have hydrogen gas on the reactant side. We're also going to want that on our product side. And right now it has the wrong coefficient as well. We need it to have a coefficient of 1, and it has 2. So we're also going to want to flip it and divide that third equation through by 2. So our third equation will be H2O gas, which we wanted that on the reactant side as well. We're going to have 1 mole of H2 gas plus 1/2 mole of O2 gas. Our delta H, we had negative 483.6. Our negative will become a positive, and we're going to have to cut that in half, so it'll be positive 241.8 kilojoules. Now if we double check everything and make sure we're left with what we want, notice our 1 mole of O2 right here will cancel with, we have 1/2 and 1/2, so that's 1. Those will go away. We're going to have our CO2, that's on the reactant side, cancel with the CO2 on the product side. And everything else we're left with is what we wanted for our overall equation. So now we need to add up the delta H's to get our sum, and they should all add up to positive 131.3 kilojoules, which that is the enthalpy for this reaction that we figured out.